Um, Welcome to the Evaporative Cooling Masterclass. As I've put in my on my introduction slide, this is almost free cooling, and we'll go through some of the advantages and disadvantages of the system, and what it does and what it can and can't do as we go through. So let's have a little look at what I'll cover today. So first of all, a little bit about mesh energy. I'm sure most of you will have heard this quite a few times now, so I will skip over that quite quickly. Then a bit about evaporative cooling, about how it works, some of the basic theory behind it. And then we'll move on to a little bit more about some of the detail and spec and design. So some of the strengths and weaknesses, some of the applications, a little bit about noise, a little bit about controls, and then one of the sort of the elephant in the room is always the Legionella risk, and people get quite hung up about Legionella risk, but it's actually pretty unusual to have any kind of Legionella problems, but it's something to be aware of. And then we're going to cover a case study. So that case study is one that I did actually at an old company I used to work for called Mekon. My boss from Mekon has kindly let me share this case study with you today, and it's for an Amazon fulfillment center, or a number of Amazon fulfillment centers where we rolled out an evaporative cooling system for Amazon, and those are all in the UK. Then finally, I will try not to scare you with too many psychometric charts, but we will cover the key points, and then how mesh work with our clients, and a little bit of time at the end for questions. So I'm hoping that the presentation will take around 45 minutes. So without further ado, let's get going. So who are Mesh Energy? Well, we are a one-stop shop consultancy for low carbon buildings. And what we aim to do is we aim to be independent, and we aim to sort of declutter the energy landscape, and give clients advice about what the best solution is for their particular application, rather than, you know, being a manufacturers can be obviously quite tied to a particular technology, and they'll always try and advise you that the best technology is the one that they happen to sell. We don't have any of those kind of ties, so we're quite independent. So we try and just be holistic, impartial, and everything else. So that's that bit done. So we'll move on to the reason why you're all here, which is to talk about evaporative cooling. And evaporative cooling is also called adiabatic cooling. And the reason it's called adiabatic cooling is because the total energy in the system doesn't change through the cooling process. What changes is the dry bulb temperature that you experience. So the wet bulb temperature stays the same, the dry bulb temperature varies, and hence it is adiabatic. And it is the most energy efficient way of reducing temperature in a space, assuming that you can't remodel the building. And we'll look a bit at the energy hierarchy further on in this. But it works really well for buildings more in the commercial sector, so places like industrial units and that kind of thing. And again, we'll look at that in the applications. And the sort of headline thing is that it can be 80% cheaper to run an evaporative cooling system than it can to run an equivalent air conditioning system. But it should be noted, of course, that you won't get quite the same performance, and that's something we'll look at further on as well. So that's what an evaporative cooler looks like. So basically, the way it works is when water evaporates, it absorbs energy. So there's energy absorbed by water as it changes from liquid water into the vapor phase. So the way to think about that is if you boil a kettle, the kettle will reach boiling point and it will sit at boiling point, and you're still putting heat into that kettle. And actually all that heat is going into converting liquid water into steam. And if you left the kettle running long enough, you would eventually boil the kettle dry. And that's basically how an evaporative cooler works, is that it's changing liquid water into vapor. So the energy absorbed from that by the water as it's turned into vapor is reducing the temperature of the airstream that's going through the evaporative cooler. Obviously, the fan within the evaporative cooler takes some electricity to run, and that's where the running cost comes from. The amount of running cost for the water is pretty much negligible. I think we worked it out. It was, a few pence a day. It wasn't, a huge amount. So let's have a sort of go at a practical example. If you take your finger, wet it in your mouth, and then gently blow on it, you'll feel that your finger feels colder. Your finger actually isn't, all you're doing actually is you're evaporating the water from the surface of your finger, and that's taking some heat away. And that's why sweating works. And other places where you experience a similar kind of thing is, for example, when you get out of a swimming pool on a breezy day, the air going over your skin is evaporating the water and making you feel a bit cool. Similarly, liquids with low boiling points, such as perfumes or aftershave, if you spray that on your skin, even from a sort of not from an aerosol, but just from a normal bottle, that evaporates. The evaporation of what's usually an alcohol in the perfume takes heat away from your skin, so you get that cooling feeling. And probably the most obvious way is if you've been exercising and you sweat. When you stop exercising, you can feel cold quite quickly, and that's again because the sweat on your skin is evaporating and taking heat with it. So how do we do that same thing on a sort of commercial scale? Well, what we do is we get what is called a wetted mat, and we pass warm air over it, and the air that comes off the far side is cooler, and the relative humidity has gone up. So that's what is explained on this slide. So a pump circulates water, and that's dropping onto the top of this mat here. It's running down through the mat. Air is drawn through by the fan through the matting and is cooled via evaporation. And I told you I wasn't going to put too many psychrometric charts in, but I'm going to put this one in just to show you that how the physics actually works. So you've got 2 points here, A and B. They're on the same line on the chart, and basically, point A, the water is at the air is at relatively low relative humidity. At B, it's at higher relative humidity, but you can see how the temperature is dropping, even though you're actually on the same energy line on the chart. And that is what is happening here, is you're moving from point A to point B on that chart as it goes through the mat. So the dry bulb temperature is reduced, the wet bulb temperature is unchanged, the relative humidity increases, and the specific humidity also increases. Okay, so now we understand how an evaporative cooler works, and they're really pretty simple things. How can we actually use this in our day-to-day work? Well, let's have a look. So first of all, this is the energy hierarchy. You'll no doubt have seen this diagram a number of times in our presentations. We always try and include it, and the reason we try and include it is that it really is the key to designing energy efficient buildings, which is what MESH is all about. So we start with the building location, orientation and form, and then we work downwards and towards the final end user at the bottom. So let's start with where we are. The building location, orientation and form, well, that may well be fixed. You probably can't change that very much. Fabric element design, well, you might be able to change that because you might be able to, say, improve the insulation. You might be able to put, say, window films onto windows to reduce solar gain. And you may be able to increase the air tightness of a building, which is normally associated with improving heat loss rather than heat gain. But but you can obviously do something with the ventilation. And that's where we're at. So we're at this third level here. So hopefully we've addressed these two top elements prior to moving down to this third air tightness and ventilation phase. So moving on from there, this slide basically just goes through what I've just talked about. and we're going to now look at the cooling hierarchy. So the cooling hierarchy works in much the same way, and basically it's saying well, you get what you pay for. And obviously what we're trying to do is we're trying to get the best balance between the cooling effect we need and the investment and running cost that we want. And that's what I'm really trying to talk about in this next slide. So on this slide, you can see at the very bottom end, we have the least amount of cooling and the lowest running cost. So that would be natural ventilation. You'll get a very small amount of cooling from natural ventilation, and you'll, as you work up through this through mechanical ventilation, you'll get a little bit more. Evaporative cooling, you can see, sits sort of just over halfway up the chart, and at the very top end you've got air conditioning. But with air conditioning comes the highest running costs, but also the most cooling. So let's have a look at some of the benefits. Okay, so we're talking generally about more commercial buildings here, so warehouses, offices, that kind of thing. So a 10,000 cubic meter capacity of cooled air may only take 1 kilowatt of electrical power. So that's in meters cubed per hour, and so 1 kilowatt hour for 10,000 meters cubed is a pretty good specific fan power, but you're not doing anything else with that electricity. You're not driving a compressor, you're not driving a refrigeration cycle. All you're doing is effectively pulling air through a filter, and then this wetting mat, and then distributing that around through a ductwork system. So from that point of view, it's pretty simple and it's pretty low power. There's no refrigerants. So from an environmental point of view, obviously we know that most refrigerants, although they're improving all the time, they do have some sort of global warming potential. Some of the older refrigerants obviously have ozone depletion potential as well. So it's great from that point of view. There's no refrigerants. There's no sort of specialist requirements in terms of having fridge engineers to come and service things, etc. Basically, we're just putting tap water into this thing. You'll always get clean air out of it. As you'll see later on, these systems always have filters upstream of the wetting mat, so you're getting clean air. Generally, that would be a G4 filter, but you can, for certain applications, so for example, for food processing plants and things where you need cleaner air still, you can obviously put higher levels of filtration on. So other benefits include the fact it's so simple, it's relatively cost effective to and easy to maintain. All you're really doing is making sure as everything's kept clean, and a lot of that is done automatically through the controls. And obviously the low running costs, so much lower than conventional AC systems. The 7 times lower running costs would be typical for a data center, where you have very high cooling demands all year round, and evaporative cooling is being used widely in new build data centers now to drive down the running cost of the data center. Cooling is usually the second highest piece of running cost for a data center after the electricity to power the servers themselves. And obviously there's not much you can do about that. That's kind of the point of a data center. So what about the downsides of evaporative cooling? Well, first of all, obviously it doesn't provide unlimited cooling because it's limited by the wet bulb temperature of the ambient air. So that's probably the most significant drawback. You can't get quite the same level of close control that you can with an air conditioning system. It does cause a rise in the relative humidity, which interestingly is actually one of the reasons why data centers quite like evaporative cooling, because if you're using evaporative cooling in a data center, it actually prevents the air becoming too dry in the middle of winter. You'd think electronics and humidity wouldn't mix particularly well, but actually, there is an optimum level of humidity, and during the winter, the data centers actually quite like having the slightly more humid air being brought into the building. And the sort of third disadvantage is obviously it doesn't work very well in tropical environments because you're relying on the air being able to take up moisture from the wetting mats. If you're a very high humidity environment, so places like maybe Singapore or other tropical areas, then it's not going to be as effective, simply because the ability for the air to absorb moisture and humidity from that wetting mat isn't there. But it works perfectly well in the UK. The absolute perfect environments for evaporative cooling are very hot, dry places. So places like Iran, I believe, has one of the highest proportions of evaporative cooling anywhere in the world. You'll also hear them sometimes in the Midwest of America, the sort of some of the western states, so places like Arizona, they're quite heavily used, and they're normally called swamp coolers over there. And obviously the other thing with evaporative cooling is because it's limited by the wet bulb temperature, the available amount of cooling reduces with the ambient temperature. However, normally cooling loads also decrease with ambient temperature, so those two things tend to offset each other. So how much cooling will you actually get? Well, this table seeks to answer that. So I'm not sure how well you can see this, so I'll just ring a few bits as we go through. So down here we've got the location. It's probably not quite as clear on the slide as it should be, and we've got a bit here that talks about the relative humidity on the hottest day of the year. So if we look at London, for example, which is obviously where an awful lot of buildings that need cooling are, on the hottest day you actually get a relatively low relative humidity of only 32%, and a highest peak temperature of 37 degrees C. So you've got quite a lot of ability there to cool the air. And typically, from a well-sized evaporative cooling system, you could get an air-off temperature of 25 degrees, which would be comfortable enough for most people indoors, which is a temperature drop of 12 degrees over the ambient temperature. So you can see here that's quite a significant rise. In coastal locations, so we've got Newquay down here, obviously Newquay down in the southwest, slightly higher relative humidity at 57%. And there you get a much more modest cooling effect of only 5 degrees. But that still gives you an air-off temperature of 20 degrees C, because the hottest day in Newquay isn't quite as warm, thanks to the cooling breeze off the sea. So again, 20 degrees would be ample for most applications. And then you can see in other areas, again, sort of Edinburgh, where you've got a high, relatively high humidity, 58%. Again, it's relatively close to the coast, and you've got the prevailing westerly wind there. You'll get a slightly smaller cooling effect of just 6 degrees there, but that still gives you a 23 degrees air-off temperature, which should be enough for most applications. So you can see it's pretty effective for the UK. So let's have a look at some applications. So here's a fairly standard type of installation, and you'll see here that we've got a roof-mounted evaporative cooler that's bringing air that's in at 32 degrees, delivering it at 26, and then you've got a set of roof fans over on the other side, which are pulling warm air out of this space, where there's obviously waste heat coming out of some of this machinery, and then taking that away. So places it might well be used are places like manufacturing environments, data centers and IT equipment areas, warehouses and distribution centers, and finally gym and leisure facilities, where again you're probably going to want to have some cooling, or at least a lot of fresh air going through most of the year round. Fresh air is obviously crucial in those kind of facilities, and people aren't going to worry too much about quite high levels of air movement. You probably wouldn't use it in a house, simply because the amount of air that you need to move to make evaporative cooling work effectively means that that you might some of the rooms, if you're sitting for long periods of time, might start feeling a bit drafty. So hence why it suits these types of applications really well, where actually you're not going to be so affected by drafts. Okay, so let's have a look. We'll talk about controls now. I'm just going to pick up to check if there's any questions in the chat. Okay, there's no questions there yet. So let me just go back to the presentation. So evaporative coolers require a few little different controls. There's nothing too horrendously complicated in there in terms of the actual evaporative cooling. What you tend to do is you then add layers of controls to these, so your evaporative cooler could replace part of your air handling system more generally. So you would, first of all, vary the fan speed, and that could be based on ventilation requirements. So you'd have probably a minimum fan speed to give you the minimum level of ventilation you require, and that could be controlled by air quality. So you could, example, have CO2 sensors, so you'll still introduce trickling air into the building even during the winter when you don't necessarily need cooling. But you could also be controlling that fan speed off internal temperature as well, so that as the building warms up, your fan speed increases. I've got a question here from Patrick. Given the high air movements is EC suitable for places such as timber mills and marble stone factories? I'm thinking from a dust particle perspective. That's a good point. Yes, you're going to get some quite high air movements, so you're not necessarily going to want to use it in dusty environments. We did do I did do a project where we used an evaporative cooler in a dusty environment, which was for it was a metal spray booth. So this was a process that was used for aerospace manufacturing, and what they were doing was they were effectively taking a very, very fine dust of copper and spraying it onto the leading edge of wings for aircraft, so that they could be used as a sort of defrosting element so you pass electricity through that film of metal that was left, and it would then heat the metal up and defrost the wings. And that was obviously a dusty environment. But what we did there is we were the spraying was going into a booth, so we were supplying the booth from the back with cooled air from the evaporative cooler, and then extracting out through the hood, and the spraying was already going into the hood. So it would probably, so the answer to your question is it would depend on what other mitigation you had in there for the dust. Assuming you're collecting that dust through some sort of local exhaust ventilation system, you should be able to use evaporative cooling for the supply air, because obviously any air that you're taking out of the building, you need to be replacing anyway, and probably your supply air requirement is going to be the limiting factor there. So I hope that answers your question, Patrick. That is exactly the sort of system that Mecon who are partners with us for this case study. That's their expertise. So if you've got any questions about that, then feel free to contact me, and I'll point you in the right direction. And obviously relative humidity control. So just going back to your to controlling the system. The final control that you'd want to have in the system would be an automatic control for the water levels within the evaporative cooler, and also the discharge and refill, and also a control to ensure that the wetting mat is dried from time to time. So what you do is you drain the water out automatically from the evaporative cooler, You then allow the fan to continue to run whilst the water is emptied out. So you're effectively moving just ambient air through the system. So you're just using the evaporative cooler as a supply fan. That in turn dries the mats inside the evaporative cooler. That gets rid of any Legionella, because the Legionella can't survive for long periods of time in a dry environment. And then when you refill the unit with clean water, that completes a sort of cleaning cycle. So that's what that automatic control is there for. I will come back to there's a question from Patrick about sorry, from Chizomo. Sorry if I've pronounced your name wrong. But yeah, I'll talk about Legionella a bit later on. So I'll get to that. Patrick, I will put you in touch with Mekon, because that's their area of expertise, is that kind of dusty environment. So I think that'll be a really good contact for you in that installation. So noise isn't generally an issue for evaporative cooling installations, for two reasons. One of which is there tends to be more of an industrial type, commercial industrial type of installation anyway. So there's probably higher levels of background noise anyway. But also there's no particular risk factors. You've basically got an air supply fan and some ductwork. So as long as you design your ductwork carefully, so try and avoid excessive duct velocities, which can lead to noise, then you should be fine. If you did have issues, it would probably be through poorly sized fan units or overspeeding the fans within those fan units. So that kind of rounds out all the positive side. So let's just look. There's one slide on Legionella, and I will go through it in a little bit of detail, because I'm conscious this is kind of a fear that people have, and it's one I want to dispel. So Legionella bacteria, for those who aren't aware, is the bacteria that's linked to Legionnaire's disease. Generally, Legionella bacteria is of highest risk when it is in very small droplets within the air. Legionella will not, you can't get, if you've got true vapor phase liquid, then so it's at steam, or sort of a highly, really real vapor in the air, then you won't get Legionella. But as the droplet sizes get bigger, then it becomes more of a risk. So that's one of the issues. And Legionella becomes a problem to humans when you start breathing in these little droplets of which contain the bacteria. So these little sort of granular things here are Legionella bacteria, seen under an electron microscope. So what can you do about it? Well, first thing you can do is you can keep the units as clean as possible. So that means changing the water regularly. It means making sure the wetting mats are dried on a regular basis, and also it means making sure that there isn't there is the small amount of bacteria in the unit as possible, of all sorts, and that you do through UV filtration. So as the water enters the wetting mat, it comes up, passes through a UV filter which kills any bacteria, and then it goes onto the wetting mat. So theoretically, the water that's going onto the wetting mat should be pretty much sterile, which obviously means that the wetting mats themselves stay clean. That, combined with regularly drying the wetting mats, helps keep the water free from contamination. The second thing is to try and ensure that the water in the unit stays below 25 degrees C all the time. That shouldn't be too much of an issue in the UK, because we rarely get prolonged periods of ambient temperatures above that, and obviously the water going into the unit would probably be at around between 7 and 12 degrees generally, so it takes a little while for that water to heat up. Again, changing the water regularly during hot periods will help prevent that Legionella growth. Then we need to ensure that we're not actually putting droplets of water out from the cooler into the ductwork system, and that is done in two ways. The first one of which is actually making sure that the wetting mats themselves are properly designed and they're the correct materials so they don't produce droplets. But the second thing is to make sure that the speed of the air going over that wetting mat is controlled in such a way that the droplets are unlikely or unable to break away from the wetting mat. And that means keeping the velocity across those mats as low as possible. And I think that the limit is 1.5 meters per second off the top of my head. And obviously make sure that the water itself is regularly replaced with clean water. Again, that will help prevent any build-up of nasties in the cooler itself. So let's have a look at the case study. So this is a case study that I carried out in my old company, Mecon. And it was for Amazon.co.uk, and they have a number of fulfillment centres around the country. And we started off by looking at the fulfillment centre in Swansea. But most of the photos I'm going to show you are actually from a later one that I was more closely involved in Hemel Hempstead. If you ever drive up the M1 and you look off to your left-hand side, you will actually see that off to your left-hand side as you're heading north, just as you come out of Hemel. So this is what an Amazon distribution centre looks like inside. So quite typically, what you will see within the distribution centre is that here on the one side of the building, you have a whole row of doors, which is where goods come in. They then go through this conveyor system. And then generally speaking, there will be another row of doors down the other side of the distribution centre where all the goods go out. And we're actually standing on what would be a picking tower here, looking down. So you can see that probably out of the whole distribution centre, usually about a third of it is the picking tower. And this is the area that we were looking at because that's where most of the people actually work. And the rest of the area is most of the distribution equipment, and there's some of the packing teams who work down, obviously, at sort of lower floor levels. So what was the issue? The issue was that in the middle of summer, we were getting temperatures in excess of 45 degrees C at the top of the pick towers. And that was a temperature that operators were actually having to work in, and it was causing issues just in terms of keeping people hydrated, keeping people healthy. And it was obviously pretty uncomfortable as well. So where was this heat coming from? Well, a lot of it actually was coming from internal gains. There's a lot of machinery in these distribution centres, and they obviously give out waste heat, and that waste heat was then rising up and collecting at the top of the building, and then not coming out. And what we found was the existing ventilation systems were simply inadequate to cope with that. So it worked. The existing ventilation system was based on having roof vents that opened once the air at the top of the building reached a certain temperature, and it would just naturally vent away. And the idea was that make-up air would come in through the open doors to make that up, and that worked fine across the bulk of the distribution centre. And it was only in the pick towers there were really issues, because obviously in the bulk of the distribution centre there's only people working at relatively low levels. So here's a sort of diagrammatic sort of representation. So we've got our pick tower on the left here, with all our little people working in it. Here's our packing distribution conveyors. They're producing waste heat, which is then rising up through the building, stratifying and collecting at the top of the building. And the problem was it was then moving into the pick towers, and you were getting this very, very high temperature in the top of the pick towers, let's say sort of 46, 47 degrees. But even down a couple of levels, it was still pretty uncomfortable. So that was basically the problem. So within the pick towers, what were the constraints? Well, the constraints were each level of the pick tower isn't actually particularly high. and they're quite enclosed. So whatever ductwork we put in had to be fairly low profile so that people weren't banging their heads on it. Each level within the PIC tower has shelving, and you can see in this photo this is quite typical of what the inside of a PIC tower looks like. You've got these shelves that are pretty narrow, pretty closely spaced. In fact, there's obviously a top level because you can't see a ceiling on there, but typically there'll be a ceiling on top of this as well. So you can see these corridors, you don't get very much natural flow of air, so they tend to trap heat. And from an operational point of view, we obviously needed to install the system without disrupting the fulfillment center's operation. So it was a pretty tricky system in terms of installation. And Mecon was commissioned to design and commission the system with the evaporative coolers and the heat extraction systems. And we actually designed the evaporative coolers for this system from scratch. So they're Mecon's own design. And this is what one of the evaporative coolers actually looked like. So this is, I think, at the Hemel Hempstead site. So you can see here we've got our evaporative cooler, which is this big stainless steel box. You can see a number of panels that you can lift away. On the outside, you can see the external air filters. The wetting mats sit directly behind them, but obviously they're not visible because they're behind the filters. Then you've got the control panel here, which is for each individual unit. There was also a master controller inside, which controlled the whole system. You can see the water supply coming out through the wall. You can see this pipe isn't insulated because with this installation, we agreed with Amazon that what they'd do is they would drain the system down completely in the winter, so there was no risk of freezing, so there was no need to insulate that pipe. You can see the drain coming off here, so there's a French drain along the bottom of this, around the plinth, and every day or so, the automatic valve in the bottom of the sump here would open and drain away any water, and then once the water drained away, there was a period of to allow the wetting mats to dry of about half an hour when the fan would run, and then after that half an hour a valve would open and allow fresh water in. Just to give you an idea of scale, this ductwork was, from memory, 1.2 meter square ductwork. So you can see the sort of scale of the system. So what was the solution? So the solution was to install a tempered air system to all floors within the PIC tower. The evaporative cooler provided that air, and that went through a series of diffusers to give an even distribution across each floor of the system. The warm air that was displaced by the cool air coming in was then forced up, was forced towards the middle of the PIC tower and then collected through a series of extract duct sort of chimneys that were then linked to roof fans. And these actually ran through the bays in the racking. So what we did is on each level, we took out a sort of 4-bay square system and then ran a sort of chimney up through that. And we ended up with a system that looked fairly much like this. So you can see that the air was supplied from the outer edges here. As it passed through the PIC tower, it would warm up and then it would be collected through this central system and then go up and out through the roof. And there were roof fans up here, and these are obviously the evaporative coolers down here. We biased the airflow so that more air was supplied to the higher levels than it was to the lower levels, and that was to account for the stratification within the building. We also rolled this out across a number of other sites. You can see this is actually for the Swansea site, where instead of using ground-mounted evaporative coolers, we actually used smaller evaporative coolers that were roof-mounted, but obviously you had more of them. And the success of this was that since that system's been installed on the Swansea site, they never experienced a temperature within the PIC towers over 24 degrees C, which was perfectly acceptable for the employees working in there. In the summer, just wear a t-shirt and trousers and boots, and they're absolutely perfectly comfortable. And because of that success, we then rolled this out across a number of other sites, including Dunfermline, Milton Keynes, Rugeley, and Hemel Hempstead. So that kind of completes the case study. So let's have a look at a few next bits and pieces. So I'm going to go through some top tips for evaporative cooling and the sort of key takeaways. So number one takeaway, always on every one of these, and you'll probably get bored of me saying it, is improve the building fabric before designing the HVAC system. Design spaces in, design services in early. I mean, the Amazon case study is a classic one. Is we ended up having to use lots of bespoke parts because we were trying to cram a system in to a building that wasn't really designed to have it in the first place. And obviously the installation took longer and was more expensive because we were trying to work around an operational building rather than, so all the installation was having to be done at night. So key takeaway, design services in early. Consider evaporative cooling where occupant comfort is crucial, and that really close control over room temperature and relative humidity isn't maybe quite so crucial. Or where cooling is a particularly high cost. So there, obviously there's huge potential for capital and running cost savings over air conditioning, and that's why you're seeing more and more evaporative coolers going into data centers. As with Amazon, where you've got buildings with very large openings or where the clients want to bring the outside air in, then that's a good application. So obviously Amazon, you've got all the bay doors open all the time. So trying to air condition that building would be very, very expensive. Cooling obviously will vary with relative humidity and temperature. So drier, warmer days will see a greater reduction in temperature than cooler, damper days. But as we said before, you also tend to get a drop in demand on those days as well. Address Legionella concerns through good design, maintenance, and controls. There is, as far as I know, no recorded incidents of Legionella from an evaporative cooler in the UK. But let's keep it that way. And finally, if you're going to put an evaporative cooler in, work out how you can combine that with other air handling requirements, so you reduce any duplication of plant. What you don't want to be doing is putting an evaporative cooling system in and then putting a separate AHU in and then having duplication of the two systems if you can avoid it. Okay, so most of you will have seen this slide before. I will run through it very quickly, but this is how Mesh could get involved in an evaporative cooling project for you. So we can obviously look at feasibility, energy and SAP calculations, and draft some space layouts at sort of the early REBA stages 1, 2, and 3. Really give you that advice on building orientation, form, etc., and help you with that sort of side of it, and then go all the way through to giving you some sort of feasibility of what you could do. Then when we're looking at stage 4, obviously design and specification, start detailing things a little bit more, and start putting together installer packages and M&E packages for you. And then finally, it's 5 and 6, get tender reviews in. So review the tender versus the specification, check that the tenders are compliant, and then provide installation oversight. And finally, at stage 7, energy monitoring, air quality monitoring, etc. Then feeding all that back so that on your next project, when we're going into 1, 2, and 3, again, hopefully there's some lessons that we can take away and some improvements that can be made. So I'm just going to go on, just before we go to questions, I'm going to go on to 2 quick shout outs. So the first one is for delivering Rebirth 2030, which is our webinar next week. Same time, same place. Really, really good one, that one. And I'm also going to introduce the MESHWORK, which is being launched in March. There is a website here, meshenergy.com/meshwork. I will put that in the chat so you can push that through. But there's now a time for questions, so I will go back through the chat. I will put the link to the MESHWORK in the chat as well, so that you can click through on that and have a look at there.
Just to let you guys know as well, the MESHWORK link will also be on the follow-up email that comes out after every webinar.
Fantastic. Thank you, Rhiannon. Okay, so let's just go back up and have a look at questions. Hopefully, Chismo, I've answered your question on Legionella with that, but please feel free to say again, to ask anything else that you want to know. Is there any good manufacturers for evaporative coolers in the UK? Well, obviously with the large scale ones we used at Amazon, we actually designed our own, and there were a number of other situations where we did that same thing. But there are companies that do that. The off-the-shelf ones that we used to use on a fairly regular basis were from a company called Eco Cooling, and they were pretty good. I know that there's a company called Colt down in Portsmouth who also do systems, so that's quite a good one to look at as well.